Welcome to the Explainer. Today, we are diving deep into a fundamentally crucial topic that literally appears in every single examination series for Cambridge Additional Mathematics 0606. Whether you're just aiming to scrape a pass or you're pushing hard to secure that absolute top-tier grade, the concepts we're laying out today are the bedrock of your success. We're going to break down examiner reports, we'll look at the exact methodologies required, and we'll translate the syllabus into clear, actionable steps you can use in your very next paper. Oh, and before we really get going, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Let's get right into it.
Okay, let's dive into this. What single missing letter ruins top IGCSE math grades? It is the absolute elephant in the examination room, and honestly, it's a trap that catches out thousands of students every single year. Picture this. You do all the hard work, you manipulate the algebra perfectly, you execute the calculus flawlessly. And then, bam! You lose an entire grade boundary across the paper because of one single tiny missing letter. It seems totally unfair, doesn't it? But as we'll see, from a mathematical standpoint, leaving out this letter isn't just a minor formatting oopsie. It actually represents a fundamental misunderstanding of calculus.
So to make sure you never fall victim to this, here is our roadmap for today. First, we'll unpack the +C trap. Second, we'll cover core theoretical principles. Third, we'll walk through the procedural framework. And finally, critical examiner insights. All right, let's start with section 1, the +C trap, and the really common mistakes students make. Here is the formal definition we need to look at. The arbitrary constant, or what we call +C, is an essential mathematical component of indefinite integrals, representing an infinite number of possible functions. Think about it this way. When you differentiate an equation, any constant number, like a +5 or a -20, well, it just turns into 0. It totally vanishes. So when you're performing an indefinite integral, which is literally the reverse process of differentiation, you have absolutely no way of knowing what that original constant number was, right? By adding the arbitrary constant +C, you are mathematically acknowledging that your answer isn't just one single curve, but an entire family of infinite parallel curves. Without it, your answer is, quite frankly, mathematically incomplete and inaccurate.
Moving right along to section 2. Core theoretical principles. These are the foundations of your success.
And this brilliantly illustrates exactly what the examiners are looking for. This quote is pulled straight from the principal examiner reports, and it says candidates referencing cross-topic connections achieve significantly higher marks. So what does that actually mean for you? Well, it means top-performing students don't just see indefinite integrals as some isolated standalone topic. They exhibit a connected conceptual understanding that transfers to totally unfamiliar contexts. They recognize how integration links up to kinematics when they're finding displacement from velocity, or how it relates to coordinate geometry when finding the equation of a curve from a gradient function. That cross-topic awareness, that is the absolute hallmark of a top-tier student. Which brings us right to section 3, the procedural framework and your technical methodology. Listen, if there is one single thing you take away from this explainer, it absolutely should be the method mark strategy. In Additional Mathematics 0606, marks are awarded for systematic analysis and process, not just the final calculation. You must prove your systematic processing to the examiners. If you make a tiny arithmetic error right at the very end of a complex integration problem, but your process was perfectly laid out and you remembered your arbitrary constant, you are still going to secure the vast majority of those method marks. Your working out is essentially your communication with the examiner. And as a quick reminder, if you're finding this helpful, definitely subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Let's look at how we guarantee those method marks. So, how do we lock in those method marks? By following this standardized sequence. Think of this as your elite academic playbook. Step 1, deconstruct the question. What exactly is it asking you for? Step 2, extract the relevant data, like specific coordinates given to help you actually find C. Step 3, select your analytical framework, meaning identify the correct integration rules you need to apply. Step 4, execute with clear notation. This means proper integration symbols, and do not forget the dx at the end. And finally, step 5, present with correct terminology, ensuring that +C is proudly placed at the very end of your indefinite integral before you move on to solve for it. Now, what's really interesting about this is the stark contrast between a standard candidate and a top-tier candidate. The standard answer often just shows a jumble of numbers leading to a final result. And here's the issue. If the final number is wrong, the examiner has literally no idea what you were trying to do, and you just get 0. In contrast, the top-tier answer follows strict Cambridge conventions. It shows proper headings, appropriate formats, clear annotation of each step, and verified results. Basically, the top candidate makes it incredibly easy for the examiner to award them marks. All right, let's move into our final section. Section 4, Critical Examiner Insights and Analysis. Top marks in Cambridge exams demand way more than just calculation. They demand descriptive, analytical, and evaluative skills. These higher-order objectives require you to evaluate alternatives, compare different mathematical approaches, and justify your conclusions. When you're dealing with integration, this might mean comparative analysis, like identifying exactly why a specific boundary condition is necessary to find your constant, supporting your steps with solid evidence, and drawing clear, logical conclusions about that final function. And here are the major warnings pulled directly from the examiners themselves. These are the top 3 mistakes you need to avoid. Number 1, using the wrong approach for the context. This usually happens when students get confused between definite and indefinite integrals. Number 2, forgetting format and presentation. We're talking missing integration signs, dropping that dx, or just writing really disorganized working out. And number 3, answers not specific to the context given. Look, if the question gives you a coordinate like 2, 5 to find the exact curve and you just leave your answer with a +c, you haven't answered the specific context of the question. You've got to stress test your work against these specific traps.
So the crucial point is this: candidates consistently confuse key terminology. Examiners repeatedly note that students mix up differentiation and integration, or they completely forget what an arbitrary constant actually represents. You need to be extremely precise. The language of mathematics is exact. By demonstrating that you understand the precise definitions, you are signaling to the examiner that you are a candidate who operates at the highest level of evidence-based reasoning.
Which brings us to our final thought. Mathematics isn't just about getting the right answer. It is about proving how you got there. That single, tiny letter C carries the weight of a massive mathematical concept. So the question is, will you leave your next method mark to chance by just rushing through the motions, or will you secure it by meticulously applying the +C framework we outlined today? Remember, every single mark matters, and your process is your power. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Thanks so much for joining me on this explainer, and I'll catch you in the next one.